Here's the answer number 28 from the energy review paper. During a rock slide, a 520 kilogram rock slides from rest down a hillside that is 500 meters long. That's the hypotenuse of our triangle, and is 300 meters high. The coefficient of kinetic friction between the rock and the hill surface is 0.25. First thing, A, if the gravitational potential energy of the rock is 0 at the bottom of the hill, what is the value of the potential energy from gravity just before the slide? Well, the potential energy from gravity equation is mgh. M was given in the problem at 520 kilograms. G is always 9.8 meters per second squared here on Earth, and the height was given at 300 meters. Here it is on our picture. When I plug all that into my calculator, I get 1.53 times 10 to the 6th joules. Next thing, B, how much energy is transferred to thermal energy during the slide? Well, we can figure that out by solving for the amount of thermal energy that happens during the slide. Well, force of friction equals mu times the normal force, and the normal force is, when you're on a hill, equal to gravity perpendicular, which is cosine of theta times mg. That was the equation for gravity perpendicular. So we know friction is mu f of n. We know mu times cosine theta mg is what that turns into when we plug in cosine or force of gravity perpendicular for f of n. And now we just need to solve for our thermal energy, which is force of friction times the distance. Because it's sliding down the hill, friction is pointing in the opposite direction, so there's no angle between the d and the force of friction, so I don't have to worry about in the work equation. Work equals force times cosine theta d. You don't have to worry about that. Just force of friction times the distance. Well, instead of putting force of friction, I want to plug in this mu cosine theta mg part, which is where this comes from in this line, and don't forget the d. Problem is we do not know what the angle of the hill is not given in the problem, so I actually had to solve for it. I know the hypotenuse is 500, the height is 300, so I have the hypotenuse, I have the opposite side, so I'm going to use sine. Sine of the angle equals the opposite, 300 over the hypotenuse, 500. When you divide those, 300 divided by 500 is 0.6, the meters cancel. But I don't want sine of theta, I want theta, so I'm going to do the inverse sine of 0.6, that's what's written right here, to get my actual angle, which is 36.87 degrees. So now I know what the force of gravity perpendicular is going to be, because I can plug in the mu, 0.25, times cosine, 36.87 degrees, times m, 520 kilograms, times g, 9.8 meters per second squared, times the distance that everything slid, which is 500 meters, which means that we have 509,599 joules of thermal energy is what's going to be created during the slide, or if you move that to scientific notation, 5.1 times 10 to the 5th joules. So that's how much energy is going to turn into thermal energy. C, what is the kinetic energy of the rock as it reaches the bottom of the hill? Well, energy is always going to be conserved. So the initial energy of the rock, which is just its potential energy because it's just sitting on top of a hill, equals the energy at the end of the problem. There's no more potential because it's at the bottom of the hill, but it certainly is moving when it gets there, and some friction took energy out of the system. So I rewrite my equation without the things that I crossed out, and here that is. Potential energy at the beginning equals kinetic energy plus thermal energy at the end. I'm solving for the kinetic energy, so I'm going to subtract thermal energy over to the left side, and we already solved for the initial potential energy, 1.53 times 10 to the 6 joules, minus the thermal energy, which we just solved for in part B, 5.1 times 10 to the 5th joules. And when I solve, I get 1.02 times 10 to the 6th joules for kinetic energy. And finally, part D, what is the speed of the rocks at the very bottom? Well, I know the kinetic energy because I just solved for it. I know that equals 1/2 mv squared. So I'm going to solve for v. I'm going to multiply the 2 to the other side, or divide by half. That's why there's a 2 times ke. I'm going to divide by the mass, so it's in the denominator, and I have to take the square root to get rid of the squared. When I plug in my numbers, I get 2 times 1.02 times 10 to the 6 joules, all divided by 520 kilograms, and that gets me a speed of 62.6 meters per second at the bottom of the hill.